Understanding transformations of functions does not have to be difficult. There's a very simple blueprint that you can apply to any function transformation problem that tells you exactly what transformations are being done to a parent function based on the way the function is written. In this video, I'm going to show you exactly what that blueprint is so that you can apply it and figure out what transformations are being done to get from F to G super easily. If that sounds good to you, be sure to stick around to the end of the video. And without further ado, let's go ahead and jump right into it and I'll show you what I'm talking about. So really when it comes to interpreting transformations of functions, like, for example, you are given some sort of function and you have to relate that to some parent function and see how you would transform that parent function to get to the function that you're given. You kind of want to think about the general kind of structure of a transformed function. And that is, if we have some function like, actually, let's not call it f of x, let's call it g of x. G of x equals something like this. So I'm just going to start by kind of writing out the general form, and then I'll talk about what it means. So in general, if you're given some function f of x, which is some parent function, so let's say, for example, what if we have like f of x equals x squared? This is a good example of a parent function. Now, this is just a standard parabola centered at the origin, right? So you have your origin, you have your parabola going up, pretty standard quadratic function, gives you that parabola centered at the origin like that. So this is a common parent function you'll be dealing with. Now, let's say we're trying to consider what sort of transformations are being done to this parent function to get it to some other function, which in this case we're calling g of x. In general, if you can kind of manipulate your function to write it in this general format, each of these parts, a, b, h, and k, will tell you exactly what type of transformation you need to apply to your parent function to get to this other function. So let me just say, for example, let's say we have some function g of x equals 5 times x, or I'm sorry, let's actually say 5 times 2 x minus 1 all squared plus 3. Something like this. So this is a great example where we have an a, a b, an h, and a k, and it tells us exactly what sort of transformations are happening there. So a key point to kind of point out here, sometimes this may take a little bit of algebraic manipulation to get the function that you're given into this format. They're not always going to be given exactly like this. Like, for example, maybe instead of this, we had 2x minus 2 all squared inside the parentheses here. So we would have to algebraically manipulate this 2x minus 2 to make it look like this, 2 times x minus 1 in parentheses all squared. Because once you apply that manipulation and get it into this form, it matches up perfectly with this form. So what do those different components tell us? Basically, you can see there's 4 pieces here. So we have an a. This a describes vertical stretching. So whatever number this a is, that tells you what factor you need to stretch your function vertically. So in this case, we have a 5 right here. That tells us we would need to stretch our parabola, our x squared parent function, by a factor of 5 in the vertical direction. So basically every point would move 5 times further away from the x-axis as it started. So then we have b. b tells us about the horizontal stretching. So in this case, we have a 2 right here. Now, the weird thing, actually, I'm not going to underline that second one. This is the one you want to be looking at. So the kind of important thing you want to keep in mind here with the horizontal stretching, this is going to work opposite of what you expect. You're actually going to stretch by a factor of 1 over b instead of, like with our vertical stretching, we stretched by a factor of a. But with b, we're actually going to stretch by a factor of 1 over b. So in this case, this is a 2. That tells us that we're actually going to be squishing our function down horizontally. It's going to be squished in horizontally so that each point on our parent function is going to move to be half as far away from this vertical axis as it started. So each point is going to move to be half as far away as it started. So we're going to be kind of squishing our function down so that it kind of becomes skinnier. And same thing would have to happen over here. We would squish it to be skinnier in this case. Okay. The next component is h. H describes our horizontal shifting. So that tells us how many units we're going to move our function in the horizontal direction. And you want to really notice here, and we have a minus sign right here. So what that means is whatever number you have here, in this case, we have x minus 1. That tells us we're actually going to move in the positive x direction to the right. So keep in mind, this sign makes it look like in the horizontal direction, we're kind of behaving the opposite of what we would expect. If we have x plus something, we're going to actually move to the left in the negative direction. If we have x minus something, we're going to move to the right in the positive x direction. So just something to really be careful of. And then the final transformation that you're going to run into a lot is this k out here. This tells you your vertical shifting. So how many units you're going to move up or down. Now with the vertical shift, when you have a +3 out here, a plus number, you're going to move that many units up. When you have a negative number, so if this were to say -3, for example, we would move 3 units down. So the way I like to remember this, your components that have to do with the horizontal direction, so your B and your H, those are going to behave the opposite of the way you would expect. So when your B is greater than 1, you would think that it would stretch your function horizontally, but it does the opposite. It squishes it horizontally, makes it skinnier. Similarly, when you have x minus some number in here, when your h basically is like looking like a negative number, x minus 1, you're going to move in the positive x direction to the right. So just kind of keep that in mind. The A and the K, however, the vertical things, so vertical stretch, vertical shift, those are going to behave exactly the way you would expect. When your A is greater than 1, you're actually going to make it longer. You're going to stretch it out vertically, making it taller. When your A is less than 1, you're going to squish it down vertically and make it shorter. Similarly, when your K is a positive number, you're going to shift up in the positive Y direction. When your K is negative, you're going to shift down in the negative Y direction. Although these types of transformation functions come up a lot in pre-calculus or college algebra, it's not all you need to know about dealing with different kinds of functions and manipulation of functions. So go click that video over there where I show you how to find the domain of a function so we can keep building on this knowledge in a way that'll really help you throughout the rest of the term or year. Might even say it's the best way to keep this brain train rolling.